Wormholes. A wormhole, also known as an Einstein-Rosen bridge, is a hypothetical tunnel-like structure connecting two separate points in spacetime. General relativity allows for the possibility of wormholes as they emerge naturally from the equations describing how gravity bends spacetime. If a stable and traversable wormhole existed, it could theoretically connect not just distant regions of space, but different moments in time as well. To make this form of time travel work, one end of the wormhole would need to be accelerated to near light speed and then brought back to its original position. Due to time dilation, a relativistic effect predicted by Einstein's theory of special relativity, the accelerated end would experience time more slowly than the stationary end. When the two ends are reconnected, one mouth of the wormhole would be in the past relative to the other. An object entering the future mouth could exit at the past mouth, effectively moving backward in time. This assumes the wormhole remains open and stable, which would require exotic matter with negative energy density, a material that has not yet been observed in nature. Time dilation from special relativity. Time dilation is a real and experimentally confirmed consequence of Einstein's special relativity. It occurs when an object moves at speeds close to the speed of light. From the perspective of a stationary observer, time for the high-speed traveler slows down. This has been observed in particle accelerators and with atomic clocks on fast-moving jets. In practical terms, if a spacecraft traveled at 99.9999% the speed of light, the crew on board would age significantly slower than people on Earth. For example, while only a few years might pass for those on the ship, decades or even centuries could pass on Earth. This allows for one-way time travel into the future. However, this does not provide a mechanism to return to the past. It is strictly forward time travel and constrained by the energy required to reach relativistic speeds. Gravitational time dilation, general relativity. Gravitational time dilation is another confirmed prediction of Einstein's theories. It states that time passes more slowly in stronger gravitational fields. The closer an object is to a massive body, like a planet, star, or black hole, the more time slows down for it relative to someone farther away. This effect has been observed with GPS satellites, which need to adjust their onboard clocks due to weaker gravity at their altitude. In extreme scenarios, if a person were near the event horizon of a black hole, time for them could slow down dramatically compared to someone far away. Like special relativity, this enables time travel into the future, not the past. The traveler could effectively skip forward in time while aging very little themselves. Cosmic strings. Cosmic strings are hypothetical one-dimensional defects in spacetime, possibly formed during the early universe. They are predicted by certain grand unified theories in physics. These strings would be extremely dense and create intense gravitational fields. If two cosmic strings were to move past each other at near light speed, or if one moved rapidly alongside a massive object, they could warp spacetime in a way that forms closed time-like curves, paths that loop back on themselves through time. A spacecraft traveling along one of these curves might, in theory, arrive at a point in time before its departure. However, no cosmic strings have been observed, and the immense energy and conditions required make this idea speculative, and quantum instability and causality violations may prevent such time loops from forming. Tipler Cylinder. The Tipler Cylinder is a theoretical construct proposed by physicist Frank J. Tipler. It involves a massive, infinitely long cylinder spinning at near light speed. According to general relativity, the intense rotation would twist spacetime around the cylinder in such a way that closed time-like curves could form. These curves would allow an object to loop through spacetime and potentially arrive in the past. For this to work, the cylinder must be infinitely long to prevent instability. Any finite version would collapse or fail to produce the required curvature. Additionally, the enormous mass and rotational velocity necessary are beyond current technological capability. Like many other time travel concepts, the Tipler cylinder remains a purely theoretical model without practical realization. Alcubierre drive, or faster-than-light bubbles. The Alcubierre drive is a theoretical model based on general relativity that proposes faster-than-light travel by warping spacetime. Rather than moving through space faster than light, the spacecraft would remain in a warp bubble, while spacetime itself compresses in front of the bubble and expands behind it. This allows the bubble to move faster than light relative to external observers, without violating special relativity locally. Because causality breaks down when faster-than-light travel is introduced, some physicists speculate that an Alcubierre drive could allow for backward time travel under certain configurations. If two warp bubbles traveled at different velocities and then interacted, closed Timelike curves might be created. However, the drive would require negative energy or exotic matter, neither of which are confirmed to exist. Quantum entanglement and retrocausality. Quantum entanglement is a phenomenon where two particles become linked so that the state of one instantly determines the state of the other, no matter how far apart they are. Some interpretations of quantum mechanics, particularly those involving retrocausality, suggest that the measurement of one particle can affect the past state of its entangled partner. Retrocausality challenges classical views of cause and effect. It does not allow for macroscopic time travel, but raises the possibility that information could, under specific interpretations, influence past quantum events. While no consensus exists, and no experiment has confirmed retrocausality as a usable mechanism, it remains an area of active theoretical exploration. Closed timelike curves in rotating black holes. Rotating black holes, described by the Kerr metric, have a region known as the ergosphere where spacetime is dragged around by the black hole's rotation. In certain solutions to the equations of general relativity, this rotation could allow for closed timelike curves, paths through spacetime that loop back on themselves, theoretically allowing time travel to the past. However, traveling these curves would require surviving extreme gravitational forces and avoiding the singularity at the black hole's core. Furthermore, most physicists believe quantum effects would destroy these curves before they could be used. Nonetheless, the mathematics suggest that if closed timelike curves exist anywhere in nature, rotating black holes are a plausible candidate.